Hello, everyone, and welcome to Lecture 17 of Computer Architecture. Today, we're going to be talking about control flow instructions. So we started talking about instructions a couple lectures ago. We're in part 2 of the course on the interface between hardware and software, the instruction set architecture. A couple lectures ago, we spoke about instructions, and last lecture, we spoke about instructions as data. In other words, how to represent instructions in memory, how to store instructions as binary. In other words, how to represent machine code. So a processor, when it executes a program, it loads instructions from memory and it executes these instructions, which means that we need a way to be able to store instructions in memory, and memory simply stores zeros and ones. So we need a way to represent instructions as zeros and ones. We looked at how to represent MIPS instructions in binary. We said that in MIPS, instructions are all 32-bit words, and there's a small number of formats for storing instructions. Particularly, there are 3 formats. And we said that this design favors regularity. When there's a small number of formats and when all instructions are the same size, this makes it easy to implement the hardware that fetches the instructions and the hardware that decodes the instructions and understands what they mean. Whereas in some other architectures, you have variable length instructions, and variable length instructions give you space efficiency and flexibility. However, they need more complex hardware because every instruction is a different size, every instruction has a different format, so that makes things more complex. So with that, formats, looked at 2 formats for representing instructions in MIPS. One of the formats was the R format, and the R format takes an opcode and a funct field that together represent what the operation is. They take 3 registers, RS and RT as source registers, and RD as a destination register. And they take a shift amount, which is only used for shift instructions. And we saw how if we have add instruction, we can represent that add instruction as in the R format. So the opcode and the funct for add were 0 for the opcode and 32 for the funct. RS, RT, and RD were S1, S2, and T0. So we looked up in the table the corresponding numbers for S1, S2, and T0. And we said that we didn't need a shift amount because add doesn't do any shifting. So we kept the shift as 0. And this was our final binary representation of the instruction. The I format, and we said that the I format is used for instructions that have one source register and either one source or either a second source register or a destination register. And they have one of the operands being some constant or some offset. And we said that this is usually used for arithmetic operations that have immediate operands, so immediate arithmetic, such as add immediate, for example, where you have one source register and an immediate value and a destination register, or load and store instructions, where this field over here is used for the offset from the base address where you're loading or storing. And we also examples of how to use the I format to represent the add immediate instruction, and then also to represent the load word instruction and the store word instruction. So with that, completes what we covered last time. Last time's material before we move on to today's discussion about control flow instructions. Does anyone have any questions? Okay, well, if there are no questions, then today we're going to talk about control flow instructions. What do I mean by control flow instructions? What I mean is instructions that help you move around in the code. I'm going to briefly go over what control flow instructions exist, and then we'll later, for the rest of the lecture, talk about where we use them. So one kind of control flow instruction is a branch instruction. And what a branch instruction does is that it branches to some instruction, so it transfers execution to another instruction, right? If some condition holds, and otherwise it's going to continue executing sequentially. Okay, So what we're either going to do is either we're going to go to some instruction if some condition is true, and if the condition is false, we're just going to continue executing to the next instruction. There are two kinds of branch instructions. There's branch BEQ, which is branch if equal, and the way BEQ behaves is that if RS is equal to RT, so it takes two registers, RS and RT. If RS is equals to RT, then we're going to branch to some label in the instruction L1, some label in the code L1. So some instruction that's labeled L1, we're going to go to that instruction. Otherwise, we're just going to continue executing the next instruction. The other branch instruction is branch if not equal. And the branch if not equal also takes two registers, but this time what it's going to do is that if these two registers are not equal, it's going to go to the instruction labeled L1. Otherwise, it's going to continue executing the next instruction. So this is how branch if equal and branch if not equal work. The other kind of instructions are jump instructions, and jump instructions are instructions that will jump to other instructions unconditionally. So a branch instruction will go to some other place in the code if some condition is true, whereas a jump instruction, if you encounter jump instruction, it will always go to this other position in the code, other instruction in the code. And there are also several kinds of jump instructions. There's the J instruction, which jumps to a label. So we have J and we give it L1, and it's going to jump to an instruction that's labeled L1. We have JR, jump register, and what jump register does is that it takes a register and it's going to jump to the address stored in this register. So instructions are data, right? Instructions are stored somewhere in memory. So every instruction has an address. So what jump register is going to do is it's going to jump to the instruction that has the address which is stored in this register. Okay, and then finally there's JAL, jump and link. And jump and link takes the label L1. It jumps to L1, but it does something else before it jumps, and we will talk about that later today. Okay, these are the control flow instructions that we're going to talk about in this course. We have two branch instructions, branch and equal, branch not equal. Then we have three jump instructions, jump, jump register, and jump and link. Okay, let's see examples of how we use these instructions. So to start, let's look at if statements. So if I have an if statement like this, if I is equal to j, I want to do f equals g plus h, else I want to do f equals g minus h. Okay, and the question is, how do I generate MIPS code for this C code over here? Well, first, the registers, each of these variables are assigned to registers, so I need to know what register each variable is assigned to. Here, this is given to us. And what we want to do is we want to generate the MIPS code that results from this code over here. So what is the first thing I need to do in assembly to fulfill this code up here? Right, if I equals j, do this, else do this. What's the first thing I need to do? Well, I need to compare I and j, right? I need to check if I and j are equal, okay? So if I and j are equal, what am I going to do? I'm going to just execute the next line of code. I'm going to execute if f equals g plus h. If I and j are not equal, then what do? Well, I can't execute the next line of code. I need to branch to the code that corresponds to the else statement. Okay, so if I and j are equal, I'm going to execute the next line of code. If I and j are not equal, I'm going to go to this line over here. So what should I use? Should I use branch if equal or branch if not equal? I'm going to use branch if not equal. You can use either, that's right. Now, if you use branch if equal, that means you need to put the else code first and then put the if code, so it's a little bit complicated. The natural thing to use here is branch if not equal, right? Because if I equals j, I'm just going to continue, all right? I'm going to branch if I is not equal j. I'm going to branch if this condition is false. So what I'm going to do is I'm going to have an instruction branch if not equal, right? The two values I'm comparing are I and J. So I and J are in registers S3 and S4. So I'm going to do branch if not equal S3 and S4. And then I go and I provide some label else. So here this label else is going to point to somewhere in the code. So I'm going to have somewhere in the code labeled else. And later on, what I'm going to do is at this else label, I'm going to put the code here that corresponds to the high-level code for the else branch. Okay. Okay, so now I've done this condition over here. If I and j are not equal, I'm going to go to the else label. But if I and j are equal, I'm just going to continue executing the next instruction. So what should the next instruction be? Well, the next instruction is going to do f equals g plus h. So how do we do that? We saw that before. What instruction do we use? Right, we're just going to use the add instruction. And here, what are the source operands for the add instruction are G and H, which are in S1 and S2 respectively, and the destination is S0. So we're going to do add S0, S1, S2. Okay. Now, after I'm done adding, when I have f equals g plus h, I'm done with this body of the if statement, or the then branch of the if statement. What do I do now? Can I just continue executing? I cannot continue executing, and the reason is that if I continue executing, I'm going to end up executing the else statement, right? Whatever code I have here for else, right? So what I want to do is, after doing f equals g plus h, I want to skip over the else code, right, and go to the end of the if statement, exactly. So, and we do this all the time, right? This is unconditional, right? I'm not after I do f equals g plus h, I'm not going to sometimes skip the else code and sometimes not skip it. I'm always going to skip the else code and go after the if statement. So what we're going to do here is we're going to have a jump instruction, jump end if, and then I'm going to put a label. I'm going to put a label end if over here after the else statement. Okay, and then finally we have now we do the code for the else statement. For the else statement, we have f equals g minus h, so that's going to be sub s0, s1, s2. And then after I'm done with f equals g minus h, now I'm just going to execute the code that comes after the else statement. So here, after I have sub, I don't need to have I can just go to the end if label. Okay. So this is how we can generate code for an if statement using branch and jump instructions. Is this clear to everyone? Does anyone have
So,
questions? Yes.
sometimes we have an if statement but without an else. Yani we execute the if statement sometimes. Yani what is in the if statement and what is outside also. In this case, we don't use jump.
Right. So if you have an if statement without an else, then this branch not equal is just going to go to end if, and then otherwise you're going to do add, and then you're going to have end if after that. So in this case, you would not have a jump to end if, and you would not have the else branch.
Okay, thanks.
Other questions? Okay. So this is how we can compile an if statement when the condition is equality. Oh, by the way, so here these else labels, this else and this end if, ultimately what this is going to be is it's going to be some address in the code. But what happens is we have two levels. First, when you have a compiler, the compiler is just going to generate these labels as symbols. And then later on, you have something called an assembler, which takes these human readable instructions and converts them to binary. And this assembler is later on going to replace the value of else with some address that that the sub instruction ends up being placed at. And we will look at this later. We will look later how we're going to encode the branch instruction and particularly this else label as a binary value. Okay. All right, so we've seen how to do if statements when the condition is an equality. However, sometimes the condition is could be a comparison, not an equality. So sometimes maybe I want to do if, rather than if I equals j, I might want to do if I is less than j, or if I is greater than or equal to j. Okay, so in this case, what we're going to do is we're going to combine branch equal and or branch not equal with an instruction we've talked about before, which is set on less than. Okay, we spoke about set on less than when we were designing an ALU. Now we're going to look at the instruction that does set on less than. So let's take a look at that. So the set on less than instruction works as follows. We have SLT, set on less than, RD, RS, RT. What this does is it's going to set RD to 1 if RS is less than RT. Otherwise, it's going to set RD to 0. Okay. And then we also have another set on less than immediate instruction. So set on less than immediate will set RT to 1 if RS is less than the constant. Otherwise, it will set RT to 0. Okay, so we have set on less than, and we have set on less than immediate, just like we have add and add immediate, and just like we would have and immediate, or and or immediate, etc. Okay. So given this set on less than instruction, now let's take a look at how we can generate code for an if statement where this time the condition is I less than j as opposed to I equals j. Okay, so here if we have if I is less than j, then f equals g plus h, else f equals g minus h. So what do we do in this case? How do we generate code for if I is less than j? Well, what I'm going to do is I'm going to combine set on less than with a branch instruction. Okay, so we don't have an instruction called branch on less than, and I'm going to talk about why later. But we only have branch equal, branch if not equal, and we have a set on less than. So the first step, correct, is that we're going to use set on less than to compare I and j. So we're going to do set on less than, right? And what are the operands to set on less than? Well, the sources are I and j, which are S3 and S4. And we're going to store the result of the comparison in a temporary, okay? So what we're gonna do is we're gonna do set on less than T0, S3, and S4, okay? So now, if S3 is less than S4, what's T0 going to be? It's going to be 1, okay? And if S3 is not less than S4, then T0 is going to be 0, okay? Now, if T0 is 1, what are we going to do? Well, if T0 is 1, that means I is less than J. That means we're just going to continue executing the next instruction. If T0 is 0, okay, that means I is not less than J. That means if T0 is 0, we're going to branch. Okay, if T0 is 0, then we are going to branch. Okay. So how do we do this? How do we branch if t is 0? Correct. What we're going to do is we're going to first have an else label that we need to branch to, okay, like we did before, and we're going to do branch if t0 is equal to 0 to the else label. So here, this is another common way of using the 0 register. You guys remember the 0 register? We don't have a branch if equal immediate, right? So the branch on equal instruction, you cannot just give it any constant. And that's why we cannot do branch if not equal 1, okay? Instead, what we are going to do is we're going to do branch if equal to 0, right? So we're going to branch if t0 is equal to 0. And in this case, we will go to the else statement, okay? Great. So if I is less than j, right, then t0 will be 1. That means this branch will not be taken, and we will continue to the next instruction. And if I is not less than j, then t0 will be 0. This means this branch will be taken, and we will go to the else condition. Okay. Now what comes next? So if I don't take the branch, I'm going to execute f equals g plus h. Well, we've seen that before. That corresponds to S0 is equal to S1 plus S2. So we're going to do add S0, S1, S2. Okay. And then what do I do after I add? So if I do f equals g plus h, what do I do next? I want to skip over the else code and go to the end. We saw that before, right? So we're going to jump. So we're going to have the end if label, and we're going to jump to that end if label. We're going to skip over the else code. Otherwise, if t0 was equal to 0, it means we're going to branch to the else, And if I'm in the else, what do? I'm going to do f equals g minus h. So S0 is equal to S1 minus S2. So I'm going to have sub S0, S1, S2. And then after I'm done with f equals g minus h, I just go to the next instruction. So I go to the end if. I don't need to have a jump over here. Okay? So this is how we generate almost the same if statement, but instead we have a comparison instead of an equality as the condition. Is this clear to everyone? Any questions? So someone's asking, is this passed to the ALU? So I don't want you to worry too much about ALU now. We're gonna, in the second half of the course, we will look all at how we're gonna do all this in the ALU. But the intuition is correct. Yes, we're probably gonna have some ALU in the processor that's doing the addition, that's doing the comparison, set on less than, etc. If we have multiple conditions, so someone's asking, what if we have multiple conditions in the if statement? Well, if we have multiple conditions in the if statement, then we're going to kind of do each of these conditions one at a time and have the necessary control flow or the AND operations that we need for these conditions. Okay. All right. Having seen this, one kind of observation is why did we do branch on equal, branch not equal only, and we use set on less than? Why don't we just have a branch on less than or a branch on greater than, or greater than or equal to? Well, the reason that it turns out that the hardware for doing less than or greater than or equal to is actually slower than doing equal or not equal. Why? Because when you do less than and greater than or equal to, you need to do a subtraction, right? Whereas when you do equal and not equal, when we design an ALU, we use subtraction for that. However, you can also design it in a different way by just comparing all the bits and checking if they are equal, right? You don't actually need to do a subtraction. So it's much cheaper to do an equal and not equal than to do a less than or a greater than or equal to. And for that reason, doing a comparison and an equal, not equal comparison and a branch on the same cycle is feasible. But doing a less than or greater than or equal to and a branch on the same cycle actually takes a little bit more time. Okay, it takes more time to do less than, greater than, equal to than equality, equal and not equal. So doing less than or greater than or equal to and the branch instruction all in the same cycle will actually require more work per instruction. So it's going to require a slower clock. Okay, and if we slow down the clock so that we can do all of this at once, what's going to happen is we're going to make all the other instructions slower. So rather than slowing down our clock, we simply do not support branch on less than, and we force the programmer to split a branch on less than into a set on less than and a branch. Not exactly the programmer, most likely it's the compiler that's going to generate the code. The programmer doesn't have to worry about it. Okay. And this goes back to our principles of making the common case fast and good design requiring good compromises. So branch on equal and branch on not equal are the common case. What we do is we accommodate the common case, and for less than or greater than or equal to, we support those using two instructions: set on less than followed by a branch on equal. Okay. Any questions? Is this clear to everyone? Okay, well, let's now take a look at loops. So we've seen how to do if statements. Let's see how we can do loops. So let's say I had this loop over here, while I is less than j, I plus equals to 1. Now, I know this is silly code. We could have just done I equals j, but I'm just showing you this code for demonstration purposes. So we have while I is less than j, I plus equals to 1. Okay, so how do we generate the MIPS code for this? And then we're going to assume that I is in S3 and K is in S4. So how do we generate the MIPS code for this? What do we do first? Right, so the first thing we're going to do is we're going to compare I and j. So we're going to do set on less than I, j, and we're going to store the result in a temporary. So I and j are in S3, S4, so we're going to do set on less than T0, S3, S4. Okay, so now if S3 is less than S4, okay, that means that means that means T0 is going to be 1. So if T0 is 1, we're going to continue into the next instruction. If I is not less than j, then T0 is going to be 0, and in this case, we're going to break out of the loop. Okay, so what is my branch instruction? Next, I'm going to have a branch instruction, right? And what does the branch instruction need to do? Well, it needs to break out of the loop, okay, if I is not less than j. Okay, how do we do that? Well, we're going to have a label. We're going to call it exit. This refers to the exit loop exit, so after the loop is over. And what we're going to do is we're going to check if T0 is 0. So if T0 is 0, that means I is not less than j. That means we should exit the loop. Okay, so we're going to do branch on equal T0, 0, exit. Okay. Okay, great. So now what we've done is we exit the loop if the condition is false. If the condition is true, we're going to simply go down and execute the next instruction. What's the next instruction? Well, it needs to be I plus equals 1. How do I do I equals I plus 1? Correct, add immediate. So where is I? I is in S3. So I'm going to do add immediate S3, S3, 1. So this means S3 equals S3 plus 1. Okay. Now that I'm done with I plus equals 1, what do I need to do? Right, I need to go back to the beginning of the loop. I need to go back to my loop condition. So which instruction do I need to go back to? Right, I need to go back to set on less than. So what I'm going to do is I'm going to put a label on set on less than. I'm going to label it loop. And then after I'm done with my I equals I plus 1, I'm going to jump to the loop label. Exactly. Okay, so this is how we generate code for the while loop up here. We do set on less than, do the comparison. We exit the loop if the comparison is false. If the comparison is true, we're going to do our addition and then jump back to our condition and do our condition again. Okay, any questions about how we generate code for loops using branches and jump instructions? Is this clear to everyone? Okay. So now that we've looked at if statements and loops, let's look at one more important thing. Now, someone has a question? So someone's asking about less than or equal to. So here what we're doing is we're kind of showing you a reduced number of instructions. Some architectures may have support for less than or equal to, but even if you don't have support for less than or equal to, what you can do is you can implement less than or equal to in terms of less than. How do you do that? So if I wanted to do I is less than or equal to j, this is equivalent to I is not greater than j. Okay, so not I greater than j. And I greater than j is equivalent to j is less than I. Okay, so if all I had is set on less than and I wanted to implement less than or equal to, what I can do it is I less than or equal to j is the same as doing not j less than I. Okay, so you can implement less than or equal to using two instructions and swapping the operands. Okay, so the next form of transferring control besides if statements and loops is procedure calling. What do I mean by procedure calling? So a procedure is just the assembly version of a function. So if I have a function at a high level, when I compile a function down to assembly, that becomes a procedure. And the question is, what do we need to do when a procedure calls another procedure? Okay, so for example, let's say I have a function foo, okay, and I compile that down to a procedure foo, and foo takes two arguments. It has a local variable, and then it calls bar. It calls another function bar. So this k equals bar and gives it two arguments. And then here I have another function bar. Bar takes two parameters. Okay, it has its own local variable too, and then bar does some work and then returns some value v0. Okay, so the question is, at this point where foo calls bar, what are the things that need to take place? So here it's not as simple as just jumping to bar. Okay, there are several other things that I need to do for foo to transfer control to bar, and then for bar to transfer control back to foo. Okay, let's see what are the things that need to be done. Well, first, foo is passing arguments to bar, so foo needs to put the values of these arguments in some place where bar knows to find them. Okay, so foo needs to put these arguments somewhere where bar can find them. So that's one. Okay. Next, after foo puts the arguments somewhere where bar can find them, foo needs to transfer control to bar. Okay, so we need to go from the last instruction that foo executed to the first instruction that bar needs to execute. And there's a catch here, which is when foo transfers control to bar, it needs to do it in a way that when bar is done, it needs to know where to return. Okay, so we'll see that later. So that's one thing. So now that foo has transferred control to bar, bar needs to begin executing. So well, bar has this local variable z, right? So what bar needs to do is that it needs to reserve a register for z. Okay. What is that? What is the, what? Why does it need to reserve a register for z? Well, let's say foo had a local variable k, and let's say foo decides to put k inside of s0. And then bar has this variable z, and bar also decides to put z inside of s0. Well, we have a problem here because here foo had k in s0. When we go to bar, bar wants to put z in s0, but maybe I need k later on in this function. Now, maybe here in this particular case, I don't because I'm storing something in k. But maybe I'm not storing something to k, and later on I need k. I can't just put z in s0. What I need to do is I need to kind of somehow make sure I don't overwrite k. So maybe I need to save k somewhere before I can start putting z inside of s0. So in general, bar needs to reserve space, needs to reserve a register for z. Okay. Then bar goes on and does the operations it does. So, if it's doing an addition, it'll do add instructions. If it's loading from memory, it'll do load instructions. If it's storing data in memory, it'll do store instructions, etc. And then finally, when bar is done, it needs to return. So what bar needs to do is it needs to return v0 to foo, right? So what it needs to do is it needs to put the value of v0, the return value, somewhere where foo can find it. Okay, so just like foo had to put the arguments a0 and a1 somewhere where bar can find it, bar needs to put v0 somewhere where foo can find it. And then after bar puts v0 in a safe place where foo can find it, bar needs to return control to foo. So somehow bar needs to figure out what is the address of the next instruction that foo needs to execute, and it needs to return control to foo. Okay, so these are the different activities that take place when a procedure, another procedure. Okay. Any questions at a high level? I'm going to talk more about how each of these things happen, but any questions at a high level about procedure calling? Okay, well let's now go and talk a little bit more about each of these. So to summarize, we have the terms caller and callee that refer to the procedure that is calling and the procedure that is getting called. Okay, so what are the steps required for a caller procedure to call a callee procedure? Like we said, there are 6 different things we need to do. The caller needs to place the arguments in a register. So the safe place we talked about is going to be a register. The caller is going to place the arguments in a register for the callee to use. Then the caller is going to transfer control to the callee. The callee is going to acquire storage for its data, so it's going to reserve registers for the data that it needs to allocate, that it needs for the variables that it needs to use. Then the callee is going to perform whatever operations it needs to perform. And then the callee is going to place the result, the return value, in a register for the caller to find. So the safe place we're going to put the return value is going to be a register in MIPS. And then finally, the callee is going to return control to the caller. So these were the 6 things that we saw on the previous slide. Okay. So what I'm going to do for the rest of today's lecture is I'm going to talk to you about how each of these things are done. But before that, I'd like to introduce more register names. So remember before I told you how we have different registers are used for different things, and I introduced the saved and the temporary registers. Well, we actually have other registers, and these are the argument registers. So registers 4 to 7, these are named A0 to A3, and these are used for storing the arguments that a caller passes to a callee. Okay, we have V0 and V1. These are returned. These registers are used as the return values of functions. We have T0 and T to T9 and S0 to S7, which we saw before. These are the temporary and the saved registers. We have GP. This register is a global pointer for static data. So we'll look at this later, but basically this register helps us access the global variables, which we're not going to see today. We have SP, which is a stack pointer. We have some stack that we use to store data on, and SP is a stack pointer that's going to be used to access the stack. And we'll talk about GP and SP tomorrow, actually. We have FP, a frame pointer that's also used with the stack pointer, and we'll also talk about that tomorrow. And then finally, we have a return address register. So RA is a return address register, and this will be used for a function or a procedure to know where to return after it's done. So we'll see that today. Okay, so these are some more, and there are more registers that I'm not listed, I haven't included here, but these are just some more of the registers that we're going to talk about. The new ones that we're interested in today in particular are the A0 to A3, the argument registers, V0 and V1, the result, the return value registers, and RA, which is the return address register. And of course, T0, the T registers and S registers, which we've seen before. Okay, so now that we've seen this, let's see what so first, a caller needs to place its arguments in registers for the callee to use. So basically, when a caller procedure calls a callee procedure, what it's going to do is it's going to put the arguments inside of A0 to A3, okay, which are registers 4 to 7. Okay, so this is how. So when the callee starts, the callee knows that this is where it's going to find its arguments. Now there's a little bit of a problem here, which is the caller itself had its own arguments inside of A0 to A3. So what it needs to do is, if it's going to pass arguments to the caller, it's going to pass arguments to a callee, it needs to save its own arguments. It needs to make sure it doesn't overwrite them. And we will look at how to do this later. Okay? Now, we said that the caller transfers control to the callee. So the caller needs to jump to the first instruction of the callee. However, to use a special instruction called the jump and link instruction. So I introduced this at the very beginning, and I told you we'll cover it later. So the jump and link instruction is an instruction that jumps, but it's different from a regular jump instruction in that the jump instruction is just going to jump to a label. The jump and link instruction, what it's going to do is it's going to jump to the label, but it's also going to put the address of the next instruction in the return address register. Okay, and we use this when a function calls another function. So when a function calls another function, rather than using jump to the beginning of the function, we're going to use jump and link instead. And what jump and link will do is that it's going to store the return address inside of a register. Okay. namely the RA register. Now there's also a catch over here, which is that the caller procedure, the one that's jumping, has its own return address register, and it needs it to, so that it needs to know, because it needs to know where it needs to return, right? So when foo calls bar, it's going to update the return address register so that bar needs to know where to return, but foo itself also needs to know where it needs to return when it is done. So it cannot it doesn't want to lose its own return address register. So what foo needs to do is that it needs to save its own return address register somewhere before it calls jump and link. Okay, and again, we will discuss where later. Okay. What's going to happen is that the callee acquires storage for its data. So as we saw in our example, bar had a local variable, okay, and maybe it wants to put this local variable in S0, but the problem is that foo was using S0 for its own local variable. So the question is, how do we make sure that the callee procedure, which is bar, does not overwrite the register of foo? What's going to happen is that if you remember, we had the T0 to T9 and S0 to S7. We had the temporary registers and the saved registers. Well, what we're going to do is, these T0, foo might be using some T registers, might be using some S registers, and bar may also want to use some T registers and some S registers. But foo is already using them. So what we're going to do is we're going to split the work between foo and bar. And this is it's the full story about the distinction between the T registers and the S registers. So what is the difference between the T registers and the S registers? Well, the difference is as follows. We're going to split the work between the caller and the callee. If the caller uses any T registers, then the caller needs to save these T registers somewhere safe before calling the callee. And if the callee uses any S registers, then the callee should save the caller's S registers somewhere safe before it uses them. Okay, and it needs to restore them before it returns. Okay, so basically, if foo is using both T and S registers, foo will save its own T registers and then call bar. If bar needs to use T registers, it can use them, no problem, because foo has already saved its T registers. But if bar needs to use any S registers, then bar has to save foo's S registers somewhere safe before bar can use the S registers. Okay? And again, I know this is very abstract, and we will do an example of this next time that will make this all clear. Today, we won't have time for the examples, so I'm just telling you what goes on at a high level, but next time we will do an example to make this all clear. Okay? Step is for the callee, so in our example, bar, just to perform its operations, so bar is going to do that. Okay? Then after that, the callee needs to place the result in a register for the caller. Okay, and again, what we said is we're going to use the V registers for that. So before the callee returns, it's going to store the results in V0, and if it needs another register, V1. Okay, so here, when bar returns a value to foo, bar is going to put that value in the V register. Okay, and then last step is for the callee to return control to the caller. So bar needs to return to foo. So in this case, what we do is we use the jump register instruction. And where do we jump? Well, we jump to the address stored in RA. Right. So if you remember when foo called bar, when the caller called the callee, right, it used the jump and link instruction. And what the jump and link instruction does is that it stores the address of the next instruction in the caller inside of the RA register. And because of that, well, when the callee is done, when bar is done, it's simply going to do jump register RA, and what this will do is it'll go back to the next instruction in the callee. So it'll go back to the next instruction in foo. Okay. So that was a quick overview of the different activities that take place when a procedure calls another procedure. And next time we will look in more detail at an example of how a procedure calls another procedure. And also I've kind of told you a lot today about, we're going to save this in some safe place. We're going to save that in some safe place. So that safe place is actually the stack. And we will talk next time about the stack and how we can save things on the stack when a procedure calls another procedure. Okay. So any final questions about today's material? Does anyone have any questions?
Sir, when the Callee returns the values in the registers, no, the local values are being cleared after it returns.
Well, we don't need them anymore. So we're just going to assume, they don't need to be cleared. But once a callee returns, the registers that it used are kind of no longer the values in those registers are no longer needed because the callee is gone. Okay, so the caller will just use them for other things.
So the registers will not be used again.
And they will be used but they will be used for other things, like, right? So for example, when the caller
I can
argument
override
is,
them.
for example, they're no longer needed by the callee because the callee has returned. So the caller will
Ah,
put its own argument registers back in the argument registers.
okay, thanks.
Okay? Yeah. Hopefully, when we do an example next time, all this will be more clear. Okay. Any other questions? Okay, well, if there are no questions, you can read more about what we covered today in sections 2.7 and 2.8. Like I said, next time we will look more at an example of how a procedure calls another procedure. Okay, that's all for today, and I will see you next time. Bye, everyone.
Thank you, bye.